All right, let's just dive right into this explainer. Today, we're exploring a massive shift that is happening right now across the tech world. We are rapidly moving away from the neat, highly organized realm of structured data straight into the chaotic, messy, and absolutely fascinating world of unstructured AI data. Which brings up a really interesting question to start things off. How exactly does AI search for a vibe? I mean, think about it for a second. Traditional keyword searches are great if you know the exact word you're looking for, but they fail completely when you're dealing with the nuance of images, the tone of an audio clip, or the complex context of human text. If you want to find a picture that just feels nostalgic, or a song with a very specific energy, a simple keyword is just not going to cut it. So here is our roadmap for today. We're going to cover the unstructured data problem, explore the map of meaning, peek under the hood, do a quick traditional versus vector database showdown, and wrap up with some real-world AI use cases. Let's get to it. Part 1. The unstructured data problem. For decades, traditional databases have absolutely loved neat numbers, exact dates, and precise strings of text. They're built for rows and columns. But AI deals almost exclusively in unstructured data. We're talking giant blocks of text, millions of pixels and images, audio waves, video frames, the whole shebang. To handle all of that, we need an entirely new tool, a vector database. Basically, this is a specialized database system designed to store, index, and rapidly search high-dimensional numerical representations of that unstructured data, which are formally known as vector embeddings. Instead of hunting for exact keyword matches, this system searches for semantic similarity. It's not looking for spelling, it is looking for conceptual meaning. Moving on to part 2, the map of meaning, or as I like to think of it, becoming the librarian of vibes. Think about your standard SQL database. It acts like a super strict catalog search. You ask for a specific title, you get it, boom. But a vector database is a completely different beast. Imagine an infinitely large 3D museum where every book ever written just floats in midair. And they don't just float randomly, they're actually arranged by meaning, tone, and context. So books about tragic romance float in one corner, while books set in the roaring 20s hover nearby. They are literally physically clustering based on the concepts inside them. So what happens if you search for something highly descriptive? Say you type in wealthy, lonely men throwing lavish parties in the 1920s. If you query that in a traditional SQL database, it is going to return 0 results unless those exact words are explicitly tagged in the metadata. But the vector database, it doesn't care about keywords. It calculates the mathematical spatial position of your request in that fluting 3D room, and it instantly fetches the books hovering closest to that exact coordinate. Suddenly, you're handed The Great Gatsby, The Sun Also Rises, and Babbitt, even if they don't share a single exact word with your prompt. It's honestly kind of mind-blowing. Okay, part 3, under the hood, the math of meaning. This whole process breaks down perfectly into 3 distinct steps: embedding generation, indexing in high-dimensional space, and similarity search. This is exactly how we translate those abstract, floaty vibes into cold, hard math. So step 1, embedding generation. An AI model, like OpenAI's text embeddings, or maybe an image recognition model like Clip, takes your raw, messy data and translates it into a long array of numbers. But, and this is crucial, we are not talking about a simple X and Y coordinate on a flat graph here. These arrays often have 768 to well over 1,536 dimensions. Each single number in that massive array represents a very specific feature or concept identified by the AI. That is an almost incomprehensible amount of detail for just a single piece of data. Once all that data is indexed in that massive multidimensional space, we hit step 3. When you execute a search, your query is turned into a vector too. The database then uses distance metrics, specifically things like cosine similarity or Euclidean distance, to calculate the literal mathematical distance between your search vector and the stored vectors. It's literally measuring the space between floating concepts to fetch the closest match, identifying what we call the nearest neighbors. Which brings us to part 4, traditional versus vector databases, the showdown. When you compare these systems head-to-head, the differences are just night and day. SQL handles structured tables and JSON, while vector databases absolutely thrive on unstructured text, images, and audio. The search logic goes from exact match to similarity and contextual matching. Your query input changes from strict SQL keys to natural language or embeddings. And fundamentally, the indexing methods under the hood are completely different. Instead of the exactness of B trees and hash indexes, vector databases use complex algorithms like HNSW, which stands for Hierarchical Navigable Small World, try saying that 3 times fast, and clustering methods like IVF. These are specifically designed to rapidly navigate that massive high-dimensional space we were just talking about. And finally, part 5, real-world AI use cases. Here are the real heavy hitters. First up, we've got Retrieval Augmented Generation, or RAG. This is exactly what gives large language models a long-term memory, allowing them to pull from private documentation to answer your specific prompts. Then there's semantic search, which powers e-commerce engines to understand actual shopping intent. We also have recommendation systems that suggest songs or movies based on vibe vectors that mathematically match what you recently enjoyed. And finally, multimodal search, where you can actually use text to search through sprawling image databases. For semantic search, just imagine typing cozy winter outfit into an online store. Because of vector databases, it doesn't just desperately look for the literal word cozy. It understands the context and brings up chunky sweaters and snow boots. Or take multimodal search. You type golden retriever playing in snow, and the database finds matching photos by comparing the vector of your natural language text directly to the vectors of the images themselves. It takes all that abstract math and makes it incredibly tangible, right in front of your eyes. Before we wrap this up, I've got a really surprising and valuable insider tip from our sources for all the developers out there. You might think you always need some massive, expensive, separate vector database cluster to do this kind of AI work. Well, actually, you don't. Modern analytical engines like DuckDB support vector similarity search extensions directly alongside your standard SQL workloads. You can execute these lookups directly on open data formats like Parquet or Duck Lake datasets. It is a fantastic shortcut for lightweight AI projects that can save you a ton of overhead. So that brings us to the end of this explainer, but it leaves us with a pretty provocative question. As you look at your own projects and this massive shift in how we handle data, are you going to be building a RAG pipeline for an LLM application, or are you exploring how to add similarity search right into an existing SQL database or lakehouse? The tools to give your AI actual context and memory are right here. The only question is how you're going to architect your next step. Thanks so much for joining me on this explainer. I hope this helps clear up the incredible technology behind vector databases, and I'll catch you next time.